I biked by the lower gates, and they were closed. I'm like, and they were plowed. I'm like, wait, they've been closed since Friday. Why isn't this plowed? They're just now doing it today.
Yeah.
It's crazy.
No, I was parked over in the library.
It's good for you.
Especially during the winter time.
Yeah, keep it level. Good for you.
I just convert my face.
I'm an artist. Yeah, they should have canceled Monday.
Seriously, or clean the gates better, right?
I don't mind. I would love it if it's
Right.
Well, in this one, we're fully made for the route for it. It was not working for it, and it's so against my old.
What I'd like to do the rest of our time together. The rest of our time together. It's like a mutant smile. I'm not excited about it. I'm not excited. What I'd like to do the rest of our time together is talk about one thing and a sub-part of that thing. And the one big thing is probability. That's the one big thing. Now, part of that was your project that you did for yesterday, or for today. That was getting you thinking, for example, like a probabilistic thinker versus a pure algebraic thinker. Okay, now, notwithstanding how you feel about the project, it's okay. Whatever you got out of the project.
I didn't mind the thing that was hard is I thought I was going to be able to use like the tree for the true-false question one.
You couldn't.
It didn't.
That's okay. You don't have to. You could have. The tree was a tool to use. The contingency table was a tool to use. Simply listing out the possibilities is a tool. Here's another way. You make me think of this right now. So Christina, notice how I put 5 exclamation points.
Yes.
In how many different smiley faces could I draw between any 2 dots in those smiley faces?
Oh my, a lot.
Okay, so let's figure it out. Ready? I could do those 2 for sure, right? I could do those 2. I could do those 2. I could do those 2. So there's those, right? I could also do this one and that one. I could do that one and that one. I could do that one and that one. Go so far? I could also do that one and that one. Or that one and that one. Or I could do that one and that one. How many altogether?
10.
There's 10.
Oh, this is like the last one.
It is similar. It is very similar, actually. It's very similar. So, do you see a pattern? 4, 3, 2, 1. No coincidence.
4, 3, 2, 1. Oh.
Good. Sums up to 10. If I added one more dot, it would go 5, 4, 3, 2, 1. Those are called triangular numbers. That's a sub-pattern of the project you just did. I didn't mention that because I want the project to go too deep, too quick. That project at least has you thinking that way now. Thinking in terms of those little symmetries and those patterns that exist in counting. Hopefully that makes sense. So that's the idea. And then you can say, how many ways can you grab 3 of them? How many ways can you grab 4 of them? How many ways can you grab all 5? There's all kinds of combinations. And that all ties into Powerball, believe it or not. That's how you figure out the likelihood of winning Powerball. It's all tied back to your project you just did. It's all tied back to that. So, one of the discussions we're having as a department about Math 105 is getting that project, if you will, the ideas earlier in the course. I might cut some more of the algebra out of this course, even though you guys didn't have very much of it in here. I might cut even more of it out and start forcing this stuff even earlier so we can go further with it later on. That's definitely on the writing block, chopping block. That's the writing block for winter term. So probability is what I want to talk about right now, and the subsection of this is called expected value. You can put that on the back burner for right now. I've already had you guys doing this without telling you because I'm a bastard. I've already had you guys doing these in class with me. It's when we take the average, a weighted average of a chart of values. That's what you're doing, is you're finding the expected value. Like for example, when I asked you, what's the average number of flips it will take you until you get a repeat on a coin? You told me 2.5. That's an expected average, an expected value, an expected number of flips. What's the expected number of flips it takes until you see all the heads at least one time, or all the sides at least one time? 3.2, I believe, is what you got, 3.2? That's because on average, it's going to take you 3.2. Sometimes it takes you 8, sometimes it takes you 12, sometimes it takes you 2. But on average, it takes you 3.2. That's what you would expect to have to flip to get that job done. I want to hit this even harder because this helps us understand casino games. Craps, roulette, chuck-a-luck. It helps us understand our insurance payments. It's all about this idea. But in order to understand this idea, you kind of have to understand this idea, because this idea gets you the weights in that column. This idea gets you the weights that you have to weight the average with. That makes sense? Hopefully it does. Maybe it doesn't. It's okay if it doesn't either. I just gave you guys some dice. I want to ask a very simple question. Might not be that simple, actually. I want to ask you a very simple question. What is the probability? Now, I'm using a word here that you might not use all that much. Probability. You can also say chance of rolling a 6. So yeah, just take one die now. Just take one. Leave the other one down on the table for right now.
118.
What's the chance of rolling a 6? I got over 118. Why? Tell me why 118.
Because you'll have 2 out of 36. Oh wait, 2 out. No.
One die, my friend. One die.
One die.
You're thinking ahead of us. You're thinking into Monday.
1 and 6.
Good for you, Ashley. Good for you, sister. You're thinking craps already. You're thinking into Monday. Ashley, what Ashley has done is she said, this die has 6 outcomes, and this die has 6 outcomes. 6 times 6 is 36. Good for you, sister. That's what we need for craps. We need that for craps. I promise you that. We need that for. But for one die,
1 and 6.
I'll vote for 1 and 6, Pam.
7.
1 and 7? Why 1 and 7? Tell me 1 and. I heard 1 and 6. I heard 1 and 7. How about 1 and 6 and a half? Call it an average. Why 1 and 7? I love this.
I don't know, because you could roll. I don't know. I don't know.
Stop asking me questions. It's 9:15. Pam, why 1 and 6?
Because there's 6 numbers on this die.
So if you look at this die, there are 6 different faces.
Right.
There's a 5, there's a 6, there's a 4, there's a 2, there's a 1, and there's a 3. So what Pam, I love this, by the way, thank you.
He's done that.
What have I done?
Both times you threw it down, you got a 6.
What's the chance of that happening? We'll come back to that. We'll come back to that in a second.
Loaded.
We're going to come back. Hey, who said that? Who said that? Good, because there's an assumption that Pam has made. See, what Pam has done is she has given us what is called the classical definition of a probability. And I love what you gave me. I love what you gave me. So what she said was, a probability is simply a percentage or a ratio. It's some kind of a fraction of occurrence of something. It's a fraction or an occurrence of something. So what Pam said was, it's the number of sides on the die. So she picked the die up and said, there's 1, 2, 3, 4, 5, 6. There's 6 sides on the die. That's in the denominator. The numerator is the number of sides that contain the number 6. Now, these have technical terms. I want to mention them now. We never have to talk about it again if you don't want to. But if, in case I drop this term on you, I want to make sure that you know what these two things mean. This up here is called the event space. And the reason it's called that, when you're talking about the probability of something happening, you're talking about the probability of an event happening. The event in this case is rolling a 6. That's what we're interested in. So you say you bet on 6. Baby needs new shoes! All you're interested in is, what's the chance that 6 comes up? If it's me, pretty good apparently. Fair enough? This down here is called the sample space. It's called the sample space. That's everything that could happen. Please notice that whatever is in the event space has to be in the sample space. Otherwise, your probability is 0. Otherwise, that's why I love the 1 in 7.
I was thinking like hitting the number twice. That's what I was
Good for you. We'll get to that. We'll get to that. That's snake eyes. That's boxcars. That's 6 the hard way. We'll get to all that next week, I promise. That's on its way. But one die at a time. It's a little bit easier, one die at a time. So that's how Pam said, okay, this is 1/6. Now, that was her 1/6. 6 faces on the die. One of them has a 6. It's 1 and 6. First things first. I want to know what that means. But first of all, what assumption did Pam make automatically and correctly, by the way, and correctly, about the number of sides on this die.
That there's six.
That there's 6 and they're equally likely. This is tricky because we grow up with dice and coins and spinners like on the Game of Life. We grow up with those things. What we don't always remember is those spinners and those dice and those coins are equally likely for every outcome. So these sides have to be equally likely to happen in order to do it Pam's way. In order to do it Pam's way, the sample space items have to be equally likely. Now the reason I bring this up is because as humans, because we spend so much time with coins and cards and dice growing up, we immediately go to things like 50-50 if there's 2 outcomes. And we go to 1/3, 1/3, 1/3 when there are 3 outcomes. And we go to 25%, 25%, 25%, 25% when there are 4 outcomes and so forth and so on and so forth and so on. That's not always correct though. Sometimes it is. Monty Hall, what's the chance you pick the right door on the first guess? 1 in 3, because the assumption is Monty's randomly putting that prize behind one of the doors. And you're randomly guessing. So you got a 1 in 3 shot at getting that door right? Good. I ride my bike home today from work. What's the chance I'm going to crash? 50-50, right? It's 2 outcomes. I either do or I don't. But I'm making a wrong assumption there, aren't I? The assumption is that it's random. The problem is I'm assuming it's equally likely that I crash or don't crash. That doesn't make any sense, right? When you next time you buy a can of Coke and you open it, there's a 50-50 chance that thing's going to explode in your face. Because it either is or it isn't. Right? But that's not true.
That's not true, yeah.
If your friend behind your back was shaking it up, there's almost a 100% chance it's going to do that. A random can bought out of a random machine is almost a 0% chance it's going to do that. When we go to the store to buy a new chick for our flock, and they've been sexed in the store, which means they're called pullets, which means they've been sexed as female, and Max grabs a girl, and I say, man, it's either a girl or a boy. It's 50-50. Not if it's sexed. If it's sexed, it's either a girl or a boy, but it's 90% likely to be a girl, and only 10% likely to be a boy. Does that make sense?
Rooster.
Could be a rooster, right? Could be a boy, could be a rooster. If you buy the chicks from someone who has raised the eggs themselves and hasn't sexed them, then it's 50-50. My wife and I had this discussion. It was so adorable. It ties back to your project, actually. It ties back to your project. Christina, speaking of your heads and tails in your project, if I may take a quick aside. Anybody keep chickens in here?
I used to.
A couple of you guys do. Yeah, a couple of you guys do. And you bought chickens. You know the 0.9. You've heard that before, I'm assuming, too. So suppose, for example, we buy 2 birds. Okay, we buy 2 birds. This actually answers your question, too, Ashley, about your rolling 1 twice or Dez's question about rolling 1 twice. That's okay, though. So suppose, let's go flipping a coin first. Flip a coin. Twice. First coin flip. This is why you could use the tree diagram for this, Christina. You don't have to, of course, but this is one way to do it. You could get heads or tails, right? And then on your second flip, you could also get heads or tails again. Heads here, tails here, heads here, tails here. Good so far? Everybody okay with this?
Yeah.
Fair? Good. Excellent. What's the chance that you get heads followed by heads?
25%.
25%? Tell me why. I love that answer, by the way. It's perfectly correct.
0.5 for each time.
Good. That's what. Can I do it another way first and come back to that? If that's okay. It's beautiful. I love that. So there's 4 outcomes once you flip the coin twice. Hopefully you're seeing them. Heads, 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 tails, tails, heads, and tails, tails. Is that fair? Those are the 4 outcomes if you throw a coin twice. So here's another contradiction to your bet what came before, right? If you get heads, it's 50-50 as to whether heads is going to follow that heads on a coin flip. Does that make sense? So, and it gets even worse as the number of sides of the coin grows out from 2. So, do you agree that there are 4 outcomes for each of these? And not any one is more likely than the other. So these are 4 equally likely outcomes. So what's the chance of flipping heads, heads? 25%, 1 in 4. What's the chance of flipping tails, tails? 25%, 1 in 4. What's the chance of flipping the same thing twice?
50-50.
It's 50-50. Because there are 4 outcomes, yes? Half of them are the same thing twice. 2 heads, 2 tails. The sample space is usually really easy to calculate. It's the event space that's the kind of pain in the butt. You have to go back in and look at the entire sample space and say, oh yes, here we have 50-50. It's right here. Yes. Makes sense? Is that fair enough? Yeah, good so far? What's the chance of flipping 2 things differently?
50-50.
The other 50-50. What's the chance of flipping heads, then tails?
25.
25%, because it's only that one. What's the chance of flipping tails somewhere in there?
1 and 3. I mean 1 and 4. Sorry.
Somewhere. Flipping tails somewhere.
Oh, somewhere?
I said
That would be all 4.
Except for that one. So it'd be 3 and 4, wouldn't it? See, you see? If you change, and this is where probability is so awesome, because I also whispered, that didn't help, I'm sure. So what's the chance of getting tails somewhere? It's either here, here, or here. It's 3 outcomes where you see tails somewhere, only 1 where you don't. 75%. You're 75% likely to see tails somewhere in the 2 flips. Is that believable? You guys buy that? Okay, good. Good. Very, very fun. And it gets more interesting as you have more and more tendrils go out. So, think about now, change this. You know what? No, don't change it. Let H equal hen, and let T equal rooster. If we bought our chicks from Lava Ridge and bought 2 of them, there's a 75% chance I've got at least 1 rooster in the mix. Don't I? Don't we? Those are my family now. Because these are the 4 alpha. Now I'm assuming that roosters and chickens are born with the same frequency, like human babies are born with the same frequency. I think that's correct. I've never been countered with that. So in other words, when a chicken lays an egg, it's just as likely to be a boy as a girl in that egg. The sexing process takes care of most of the boys. Is that fair?
Right. In the human population, the only reason why there are a few more women than men is the survival rate's better.
Oh, okay. But how about the birth rates? Are they 50-50?
I think not,
Arguably,
because I
no.
think maybe, well, I guess live birth rate, I don't think
No,
so. I
not
still think-
necessarily, just birth rate. What gender?
I'm not sure. Yeah.
No, I'm not sure either, Amy.
Yeah.
What Amy's bringing up is the age-old question I have no good answer for.
Why are there more women?
Why are there more women than men? And you have to ask yourself, okay, you talking about being alive or being
Right.
born? I like the alive analogy.
Survival.
Guys die earlier than women on average. That's just kind of a fact. We know that. Whether it's biological, whether it's environmental, whatever. Does what have to do with it? War used to have to do with it a lot. With the Civil War and World War II and things like that, a lot. But there are such a smaller percentage of people going to war now, and women are in the service now, that I think that's beginning to catch up and even out again. But what I'm more interested in is the birth gender rate. Like born. Tiff, you know?
Well, they say that females are born more because it takes a lot more to make a meal.
I've heard this.
Yeah.
If you look at certain populations besides humans, a stressed population will create more females than males because of that. It takes a lot of work to put that Y chromosome in there, apparently. We're a pain in the ass, we are. Yeah? So stress, especially with stress, I often ask this question. I say it to my 243 classes, like, you know, parents of daughters are more likely to be divorced than parents of sons. So does this mean if you and your spouse have a bunch of daughters, you should worry about divorce? And it makes the kids stop for like 5 minutes. They're like, holy shit. They're like, I have 3 sisters, you know? And then we have this discussion that it's not that the daughters caused the divorce necessarily. It's that the stress that's contributing to the divorce also contributed to the human body trying to conserve energy. That's why you had 2 girls. I'm not saying anything, Christina. I just saw on camera. But Tiffany, I've heard the exact same thing. Very good. But the question is, in lieu of that, if we take that stressor out, should the birth rate be 50-50? I see no reason to think it shouldn't be.
Well, I was going to say, biologically speaking, that when we're talking about evolution of species will naturally create more women because women can produce babies. Men can have more than one mate.
Yep.
Men can have more than one mate and make more babies, but women can only
But
have...
now human species behavior, that's the theory. What's actually happening? Because men can have more than one mate, but that's kind of frowned upon in many cultures.
Right, but I'm talking about evolutionary speaking, like evolution.
No, but again, now, we're taking the net a little bit too wide. That's okay. But I guess what I'm saying is there any reason to think it's not arguably 50-50 for chickens?
No.
Then we'll just leave it 50-50. Okay, I see what you're saying, Jerry. I love what you're saying, actually. It makes a lot of sense. Mother Nature is wickedly efficient. She is. Wickedly efficient. But we also fight Mother Nature every chance we get as humans. And because we're now breeding chickens for eggs or for whatever, for meat, then... do we eat the boys and the girls? Or is it just the girls we eat for chickens?
I don't know.
I've eaten rooster before.
Have you? Is it yummy?
Is it the same?
They're bony.
I don't know.
It's just bonier. It's not bad. It's just
Tastes like chicken.
not as bad.
Ha!
Usually
Tastes
when
like
you
chicken.
kill a rooster, you eat it.
It's gotta get a pound too. This is brilliant.
No, they're just bonier.
Okay. Well, but I guess my question then, we probably have messed with that number too. Since if we want more girls, we probably changed it so that we somehow zygote make more girls. I don't know. Let's call it 50-50 just for the sake of argument. So you can see that there's now a 75% chance that I got a rooster in my batch somewhere. If I don't want roosters, that's a problem. It only gets worse with every additional bird that you buy. Because imagine what's going to happen. If I buy a third bird, these are all going to split HT, 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 HT. Only one of them is going to be HHH, isn't it? The top one, HHH. Every other one is going to have at least one T in there, including the one at the bottom that goes TTT.
Biology 101.
It is! It's like Bio 101 all over again, about the Punnett square. So, I told my wife, I was like, babe, let's not buy the chickens this way. Because I don't want to deal with the high likelihood of at least one rooster. So here is where Dave's idea came in. I love this, by the way. He said he did 0.5 times 0.5 to get 25%. 0.5 times 0.5 is 1/4, right? It's a half times a half, which is a fourth. A half times a half, which is a fourth. A half times a half, which is a fourth. And a half times a half, which is a fourth. Is that fair? But with chickens, it's not like that. It's 0.9, 0.1. 0.9, 0.1, 0.9, 0.1.
You mean after they've been sexed?
This is after they've been sexed. When you go to the store and you buy these little pullets, as they're called, out of the store. So now, if I buy 2 birds, what's the chance I get 2 girls? It's 0.9 times 0.9, which is 0.81. Those are pretty good odds. That's pretty high. That's almost 100%. The highest probability you can get is 100%. That means it's going to happen. If they had a 100% sexing rate, I'd have a 100% chance of getting 2 girls if I bought 2 birds. Because there'd be no question, I got two girls. But there's never 100% with sexing. There's always a chance of error, chance of genetic anomalies that miscue the sex, or even if they're really, really good. What's the chance I get a boy and a girl? Well, there's 2 ways that can happen. This one could be a boy, this one could be a girl, that one could be a boy. That happens 9% of the time. Or vice versa. This one could be a boy and that one could be, which also happens 9% of the time. So there's a total of 18% chance of getting a boy and a girl. That's still pretty high. That's still pretty high. That's 1 in 5, just about. But all of a sudden, the chance of getting 2 roosters is out the window. 0.1 times 0.1 is 0.01. This adds up to 100%, doesn't it?
Yeah.
As it has to. If you buy 2 birds, that has to happen. There's a 100% chance of one of those 4 things happening. But because these have now switched, the underlying probabilities have switched. Now, I'd like to back away from that for now and keep everything equally likely on the dice for now and get back in. I love getting into this. And a huge chunk of 243 is dealing with this. I just had the kids do a quiz. I want to see how they liked it next class. Guaranteed way to make $1 in Vegas. Guaranteed way. I can promise you a guaranteed way of earning $1 in Las Vegas. It's pretty simple. Just go in to play craps. Bet $1. If you win, they pay you 2 to 1, go home. You want $1. If you lose, double down. Pay $2 more. Now you're in the whole 3. If you win, they're going to pay you 4 though, because you bet 2 to 1 payout. So you bet. They gave you 4. You bet 3. You cleared $1. Go home. You want $1. If you lose, double down again and bet 4. Now you're in the whole $7, right? But you bet 4. So if you win, they're going to pay you 8. If you win, you paid you 8. You paid 7. Your profit $1. Go home. If you lose, double down again. It's a guaranteed way of winning $1 in Las Vegas. Anybody see the problem with it?
How long do you have to
Yeah.
It just cost you $8 to win 1.
Yeah.
Yeah.
So you won $1, but it also cost you $8 to do so. I often love having this discussion with people, not in gambling terms, but in other terms, like, you know, like, oh, I bought this house in 1986 and I did blah, 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 and I resold it, we profited $10,000. I'm like, yes, but you put $80,000 into it. Yes, but, and they stop. Yes, but, like, you gotta look at inflation. That makes it even worse. That makes it even worse. Anyway, point being is look at all those little factors, right? You made $1 at what cost to yourself, right? What's it? There's an old, oh, like fable, not fable, but say, idiom. What is it? Oh, poop. It's got like a nickel and a dime. Oh, I can't remember it now. It actually ties up that idea. I can't think of it right now. Poop. That's all right. It's not poop. That's not it. Anyway, we'll come back to this. Let's go back to the dice. So Pam, thank you. Thank you very much for the 1/6. I know you said that like 20 minutes ago, but I want to come back to it now. So what Pam just gave us is what's called the classical definition